The math we learned first, the basic counting numbers, operates very much like a rigid structure of physical space. This is the integer set, denoted by the letter z. It is a highly ordered, discrete space, where every value is distinct and occupies a specific, fixed position. In this set, numbers follow a strict rule of adjacency. For any integer m, there are immediate neighbors at m plus 1 and m minus 1. In z, the space between 22 and 23 is empty space. This logic holds until we attempt to divide. If we try to plot 19 divided by 5, the operation falls through the grid into the void. To represent these missing quantities, we define the rational number set, q. These are values expressed as a ratio of two integers, p divided by q. Entering this new set requires us to abandon the two defining rules of integers. In q, we lose both the guarantee of a unique name for every value and the concept of an immediate neighbor. Understanding rational numbers requires looking past the rigid, stepped logic of integers and adopting the fluid rules of a mathematically dense space. In the integer set, every value has one name. In base 10, the quantity 7 is only ever represented by the digit 7. The set q operates differently. Consider this coordinate point representing the fraction 3/5. If we multiply both the numerator and denominator by 2, we get 6/10. Despite the different digits, the mathematical value is identical, occupying the exact same position on the line. We can repeat this by multiplying by 10 to get 30/50. Because we can multiply by any integer, a single coordinate can be represented by an infinite number of different fractions. We need this flexibility to perform arithmetic. If fractions were locked into a single form, we couldn't align different denominators for addition or comparison. For example, comparing 3/5 and 3/4 is difficult because the denominators, 5 and 4, measure different units. We solve this by finding common multiples. By scaling them to 12/20 and 15/20, we can see that 15/20 is clearly the larger value. However, this creates an identity problem. If one coordinate has infinite valid names, we lose the one-to-one relationship between a number and its representation. To fix this, we need a standardized process to strip away these extra layers and find the absolute core of a number. This core is called the reduced form. It occurs when the numerator and denominator share no common factors besides 1. Take the fraction 18/60. To find its reduced form, we have to look at its internal components. We use prime factorization to break the numerator and denominator down into their most basic, indivisible building blocks. For the numerator, 18 factors into the primes 2, 3, and 3. The denominator, 60, breaks down into 2, 2, 3, and 5. To reduce the fraction, we identify the matching primes that exist in both the top and the bottom sets. We find 1, 2 in both trees. We also find 1, 3 that exists in both sets. Multiplying these shared factors, 2 times 3, gives us 6, which is the greatest common divisor for this fraction. When we divide 18 and 60 by this divisor, the common factors cancel out. This leaves us with the remaining primes, 3/10. 3/10 is the unique canonical version of this number. The numerator and denominator now share a greatest common divisor of 1. While integers are born unique, rational numbers must be algorithmically reduced to reveal their simplest form. Beyond representation, the set q differs from integers in how the numbers are spaced. In z, if m is 22, the next number is 23. There is a definitive step from one to the next, with no integers between. But if you are at a rational number, m/n, what is the next fraction? It turns out that in the rational set, there is no such thing as a next number. We can prove this with the arithmetic mean. Take two distinct rational points on a line, m/n and p/q. Calculating the average of these two values creates a new point located exactly equidistant between them. Because this average is derived from integers, the result is itself a valid rational number. This process can be repeated infinitely. You can always find a new midpoint between any two existing points, forever generating more fractions in smaller and smaller gaps. This property is called density. A set is dense when, between any two numbers, no matter how close they seem, you will always find another number. This contrasts with the discrete topology of integers, which is defined by the gaps between points. Because you can endlessly subdivide the distance between points, a true next step cannot exist in Q. Every rational number is separated from its neighbor by an infinite number of other values. The integer set Z is a discrete world built on absolute uniqueness and fixed steps. On the right, the rational set Q is a fluid continuum where values can be expressed in infinite ways. Transitioning to rational numbers replaces the rigid, stepped architecture of integers with a topology where division is possible at any position on the number line. In this environment, we lose the simplicity of a defined numerical sequence. We manage this density by using the greatest common divisor and prime factorization to find a single, standardized representation for any given value. To move into advanced mathematics, we must accept that true numerical space is infinitely dense, possessing no empty gaps and no definitive next steps.